Video we're going to talk about molecule polarity. In the last video we talked about bond polarity, what makes a bond polar or non-polar. And we talked about the electronegativity difference between the two atoms in the bond. The bigger the electronegativity difference, the more polar the bond. For a molecule to be polar or non-polar, there's another set of rules here. I like to look at symmetry. It makes it a little easier for me. If the molecule is completely symmetrical, meaning all of the peripheral atoms are exactly the same atom, and there's no lone pair on the central atom, then the molecule is immediately tagged as nonpolar. So nonpolar molecule versus polar molecule. A nonpolar molecule is symmetrical. And the term symmetrical means all the peripheral atoms are identical. All of the atoms on the outside around the central atom are all chlorines or all fluorines or all hydrogens. Okay. Also, a nonpolar molecule tends to have no lone pairs on the central atom. Okay, well, what about a polar molecule? A polar molecule tends to be unsymmetrical. Or it tends to you see a lone pair on the central atom. All right, so I'm going to put a couple of molecules up here for you, and let's try to use this to figure it out. Let's say I have ammonia, NH3. That's the Lewis structure for ammonia. It's a tetrahedral electron arrangement, trigonal pyramidal shape or molecular geometry. Can you see that you have 3 hydrogens here? So you would say, oh, it looks symmetrical, but no, you've got this lone pair, so therefore this is polar. Okay, here's another one. Let's say I've got this one. Okay, so I have a carbon with 3 fluorines around it and 1 hydrogen. What do you think, polar or non-polar? Definitely polar. Why? Because it's unsymmetrical. The peripheral atoms are not identical. So this is polar. Did you get the idea? This is honestly the easiest way of looking at molecules and figuring out if they're polar or non-polar. Your book shows other techniques, but I found in all of my years of teaching, this works perfectly fine. Okay. So you should be able, if I give you a molecule, you should be able to find its Lewis structure, be able to tell me what the electron arrangement is, be able to tell me what the molecular shape is, and then be able to tell me if it's polar or non-polar based on everything we've talked about. Okay. One thing about shapes and geometry, what if you have more than one central atom? So something like this, for example. This happens to be a molecule of ethanol or alcohol, ethyl alcohol. See, this is a central atom, this is a central atom, this is a central atom. So what you do in a situation like that, and you might see stuff like that in your homework, is that you talk about the shape around each central atom. So around this one, it's tetrahedral because you've got 4 electron dense areas with no lone pairs. Around this one, it's also tetrahedral. 4 electron dense areas, no lone pairs. Around this one, you see that you've got 4 electron dense areas, tetrahedral, but you have 2 lone pairs. Remember, that would be bent angular. So the shape around this is bent angular, shape is tetrahedral, shape is tetrahedral. Okay, the last thing in this chapter, this covalent bond model, deals with naming covalent compounds. naming covalent compounds. I don't know if the green shows up. It doesn't show up very well. Let me stick to the black or the blue. Okay, so the big difference between ionic compounds and covalent compounds in the name is that you have to use prefixes in the name of covalent compounds. You must use prefixes. What do I mean by prefixes? Well, if you have two of a specific element, you have to use the prefix di. If you have three of a specific element, you have to use the prefix tri. 4, tetra. 5, penta. 6, hexa. Sometimes you drop the the A if you have a vowel, so it'd be hex oxide, not hexa oxide, because A and O, you end up dropping the A. 7, hepta. 8, octa. 9, nona. And 10, deca. And 1 is mono, but we don't really use that a lot. You only use mono if it's for the second element. And I'll show you what I'm talking about. Let's say you have this. I'm making it up. There is no such element, but I'm just making, and no such molecule, but I'm making it up. For this, you would have to give the full name of the first element and then use the prefix di. So you're going to write di nitrogen. And then the second one, remember how with ionic compounds you end it with an "ide"? You do the same thing with covalent compounds, but you have to tell me that you have 5 of them. So it would be pentaphosphide. You see what I'm doing here? All right, let's try another one. I'm going to erase these. This would be carbon. You don't use mono for the first one. You only use mono for the second one. This would be carbon disulfide. Okay. What about this one? Nitrogen dioxide. Okay. What about this one? Carbon tetrachloride. Okay. So with covalent, and first of all, how are you supposed to know that they're covalent or molecular compounds? 2 nonmetals. It's always going to be 2 nonmetals. If I trick you and then all of a sudden put this in there, many of you will say barium dichloride, but no, barium is a metal. This is a nonmetal. This is an ionic compound. With ionic compounds, you never use prefixes. So this is just barium chloride. Okay, so that does it for nomenclature. You don't use prefixes for ionic compound. You use prefixes for covalent compounds. How are you supposed to know that they're covalent? You notice that you have 2 nonmetals. Oh, and one other thing, hydrogen, you tend not to use prefixes with hydrogen. So you don't say dihydrogen sulfide. This one you just say hydrogen sulfide. Okay? The mono honestly is used more with oxygen. So like this would be carbon monoxide. Okay? I think that covers pretty much all the important stuff in the covalent bond model. And we are all set for all this topic. Okay, good.